Hello once again, class, and welcome to another mock lecture. We are finishing up the Math 111Z prereq stuff with a quick quadratics recap. So we're going to start off with the anatomy of a parabola. First of all, there's two different ways that you could write a parabola just in general. One of them is called the standard form, which is your classic ax squared plus bx plus c. That's the worst straight line I've ever drawn. The second one is the vertex form, which is a times the quantity x minus h squared plus k, where h and k are actually the coordinates of your vertex, which I'll show you guys here in a second. When you graph these things, you get a shape that's called a parabola. Now, parabolas either open up or open down depending on whether a is less than or greater than 0. If it's less than 0, then your parabola is opening down, where the vertex, the apex of the parabola, the turning point of the parabola, is a maximum. But if it opens up when your leading coefficient is positive, then that turning point ends up being a minimum of the graph. Parabolas are also symmetric across a vertical axis that runs directly through their turning point. And again, that turning point is called a vertex. Now in vertex form, like I said, you get to see what the vertex is. So if I have like 4 times the quantity x plus 3 squared minus 7, then the vertex is actually -3, -7. -3 because in the normal formula you have x minus h, but here we have x plus h, so h itself must be negative to turn this into a positive. If you have a function in standard form, then you actually have to calculate the vertex using the vertex formula, which is actually different than the vertex form, which is oftentimes confusing. But the vertex formula is a way to really just calculate the x coordinate of the vertex, and then you take that, you plug it back into f to get the y coordinate of the vertex. But in either case, you can find what the vertex is, which is oftentimes really important when you're graphing these things. The x-intercepts of the graph are solutions to where your function's set equal to 0. And actually, that's maybe the first really important thing that I want to point out. X-intercepts of a graph are the same thing as solutions to when its equation is equal to 0. So zeros and solutions are kind of synonymous in that sense. There's a very famous formula that actually helps you calculate the x-intercepts, or the zeros, of a parabola specifically, and that's the quadratic formula. -b plus or minus the square root of b squared minus 4ac all over 2a. Now, when you solve, and maybe you do solve with the quadratic formula, 3 things can happen. The first is that you get a graph that looks like what we have in our example. Well, they don't always open up, but the point I'm trying to make here is that you end up with 2 x-intercepts, or 2 real solutions, right? Remember, those are the same thing. X-intercepts, real solutions, those are the same. The second thing that can happen is you could get 1 real solution, right? So I'm talking about this one. And that would happen when your vertex is on top of the x-axis. So it's coincident with the x-axis only at that one point. And so that's where you'd have 1 real solution or 1 x-intercept. And then the third thing that can happen is that your graph could have no x-intercepts at all, which means it also has no real solutions, but it does have 2 imaginary solutions. So I is going to be involved, which you can't see on the xy plane since it's only graphing real numbers. All of these cases, by the way, come from what's called the discriminant of the quadratic formula. It's the thing that's underneath the square root. When that thing is positive, then you get 2 answers, 2 real answers. When it's 0, you only get 1, because the square root of 0 is only one thing, it's only 0. And if it's negative, well, then you get imaginary stuff, because you can't plot imaginary numbers on the Cartesian coordinate system. But let's talk about solving. So one way that you could solve is, in fact, with the quadratic formula. Students are going to have their own line where they're like, okay, I guess I'll use the quadratic formula. My line is, if I don't see how to factor it like within the first 15 seconds of looking at it, then I'm like, okay, I'm just going to use the quadratic formula. Because for me, solving, I try to do whatever the fastest method is. So sometimes that's factoring, sometimes that's quadratic formula. Sometimes it's using a different method. In this case, I think this one's maybe worth considering factoring because c is a prime number. Like, remember, factoring is all about organizing factors of your leading coefficient in the first 2 spaces of a binomial and factors of your constant in the second space of each binomial. But there's only one way to organize factors of 7, right? Initially. You could do 1 and 7. You know, both of these are actually, in fact, even going to have to be negative because b is negative, but these things need to multiply together to give you a positive. So like all of these things I'm thinking about, and I'm like, well, should I try to factor or should I not? There's not many things to try, actually. You could put 2x here and 3x here, put 3x here and 2x here. You could try 1x and 6x, or 6x and x, and that's pretty much it. But in thinking of the discriminant, I actually already see this is going to be imaginary. Like b squared minus 4ac is going to be negative stuff. So we can't factor this, at least not traditionally. We're going to end up with imaginary solutions. But anyway, all of that to say, use the quadratic formula wherever you feel comfortable. If that's your go-to method all the time, that's fine. I would encourage you to try other stuff, and I'll show you what I mean here in the next examples. But, you know, the quadratic formula does work for everything, so sometimes students only want to memorize one way to solve, and that's the one way, and that's fine. Anyway, that was a massive tangent. Using the quadratic formula, we need to assign a, which in this case is 6, a b value, which in this case is -4, and a c value, which is 7. And again, remember, they're just coming from this in the standard form. And then you plug it all in to the quadratic formula. And this is the part that I just personally find super annoying, just like simplifying all this stuff. Not a whole lot's going on here, though. I'm just simplifying. I stopped here actually not because we're done, but because I want to actually talk about this. This is still not simplified. Oh, and I guess the other thing to point out is, you know, 16 minus 168 was -152. So the way that I dealt with the negative sign is I just brought out the I in front of the radical. But that's all, you know, that's the only special thing that I've done so far in all of this stuff. But you do want to try to simplify your solutions when you can. And the square root of 152 does simplify. So if we simplify 152, what I do is I make myself like a factor tree. So like a 2 comes out, it's even, right? You get 76, I think it is. Well, we're going to see here in a second. 76 divided by 2, which can be done because it's even as well. So you get 38 there. Then this goes into 2 and you get 19. I have it in the next slide. Yeah, okay. So when you're simplifying this, anytime you're able to pair up numbers, one of those numbers comes outside of the radical and you're left with whatever didn't pair up. 2 and 19 didn't pair up, so that's why there's still a 38 underneath the radical. But I took the square root of 4 essentially to bring this 2 out. And so this became this. And now 4, 2i root 38, and 12 all have a 2 in common, so I simplified everything by a factor of 2. And now that's my answer. So again, quadratic formula, you draw your own line. You could do that for everything. It does get annoying and a bit tedious at times, which is why I like to encourage students to try and factor. Factoring is a method that, you know, obviously is not going to work on everything. But again, whenever this or this is prime, I at least try to think about it. So remember that the game that you're playing here is you're trying to put factors of your ax squared term, which in our case is 3x squared, into the first position of each binomial. And then you're trying to put factors of your c term into the second position of each binomial. 3 is a prime number. So the only way you could break that up is with 3 and 1. So I put 3x in the first position of the first binomial and x in the first position of the second binomial. Now I just need to figure out how could I organize 10 into these spaces here, factors of 10. Well, the factors of 10, oh, and also I put b is positive and c is positive, so I know for a fact these have to be plus signs inside the binomials. There's only 2 factor pairs for 10, 1 and 10 and 2 and 5. And so organizing them in each binomial makes it so that there's only really 4 things to check, which isn't bad. And honestly, I would argue you don't even need to check the first one, right? If you do 1 and 10 here, that automatically gives you 30 x's. And we're trying to get 17 in the middle after we FOIL. Because that's the game. We want to organize factors of 3 and 10 in the last 2 spaces such that when you FOIL, you get whatever b is. And in our case, it's 17. But anyway, 1 and 10 isn't it. You could try 10 and 1. This is going to give you 3x and 10x, and when you add those together, you get 13x, which is close, but still not 17. And then the very next one you try is 2 and 5, and that one actually does work. This is 15x plus 2x. that's 17 x's, and so, okay, that's the one. So let's lock that in. Now, once you lock it in, you use what's called the zero factor property, which says that if you have two things, A and B, that multiply together to give you 0, well, then either A is 0 or B is 0. For us, A is 3x plus 2. B is x plus 5. And it's equal to 0. So I set 3x plus 2 equal to 0, or it's x plus 5 is equal to 0. And then I just solved them individually using just solving an equation in one variable. And I got my two solutions. And remember, that represents the x-intercepts of our graph. So let's pretend here's -5. Let's pretend here's -2/3. It's opening up because it's positive. So our graph probably looks something like this. Something like that. That is a terrible shape of a parabola, but there you go. Now, if you don't like guess and check factoring, there is a more methodological factoring method that is factoring by grouping. I'm not going to go through this, but if you want to pause this here, you can feel free to kind of reason your way through it. Maybe I'll do a factoring by grouping video sometime at a later date. And then the third method is with square roots, which is the most exclusive method that exists for solving quadratics, in the sense that you can only use it on two types of problems. It's either the case that your equation is given in vertex form, or there's no bx in the problem, right? Like this term is missing. And that's the easiest one to deal with. Just isolate the x squared and then square root. So that's what I got here. X squared is equal to -2. I square rooted both sides. You always have to keep in mind the square root property, which says when you square root, you introduce a plus or minus. But I ended up getting plus or minus I root 2. Now you can certainly use the quadratic formula and you'll get this, but this is significantly faster. The other one is when you have it in vertex form, you just, again, you isolate the thing that's being squared, which I did here. I'm going to get 4 when this is all done. And then I'll take the square root of 3x minus 5 quantity squared. That'll give me plus or minus 2. And then I had 3x minus 5 on this side because the square root undoes the square. And then I just solved. You don't want to leave your solution like this when possible. Like this represents two things. It's 5 plus 2 over 3 and 5 minus 2 over 3. This is where I got 1, and this is where I got 7/3. So again, try other stuff. That's my encouragement. Try other stuff before you use the quadratic formula. And then finally, I just wanted to leave you with some other strategies. And basically what I want to point out here is keep in mind that your quadratic equation is an equation. So when you see things like fractions that you want to get rid of them, right? Multiply in this case by 12. It'll turn the 1/3 into 4. It'll turn the 1/4 into 3. It'll turn the -1 into -12. And then 12 times 0 is still 0. But now this doesn't have any fractions in it. Easier to solve. Use quadratic formula, or maybe you can factor that one. Same with this one. You have decimals. Well, you can move a decimal space by multiplying by 10. I want to move this one twice to make that a whole number, so I'll multiply by 100. 0.14 becomes 14, 0.03 becomes 3, and 1.5 becomes 150. At least they're whole numbers. And then finally, always look out for this type of, I feel like textbooks try to trick students into thinking, oh, we can just do this. But there is no 8-factor property. There's only a 0-factor property. So this is going to require us to expand this, FOIL method or box method, then move the 8 over to the other side, and then refactor. So I got x minus 6 times x plus 3, set each of those equal to 0 using the 0-factor property, and I got 6 and -3. Okay, so that's it for this one. Just wanted to really quickly recap some quadratic stuff. Hopefully this doesn't turn out to be too long, but that's kind of where we're going to start. We're going to move into polynomials next, and so it's crucial that we understand what's going on with quadratics. If you guys have any questions, please drop a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.